Welcome you all. Myself, Miss V.B. Mani, working as an assistant professor at Satara College of Pharmacy, Satara. In this video, we are going to see effect of solvent on absorption maxima of paracetamol. The aim of the experiment is to determine effect of solvents on absorption spectrum of paracetamol. After performing this experiment, these four types of the objective will be achieved. So this type of the glasswares, chemicals and instrument will be required before going to proceed for this experiment. Now we have to see the principle involved in the determination of the effect of solvent on the paracetamol. A most suitable solvent is that solvent itself should not absorb in the range under investigation. A dilute solution of the sample is always prepared for the spectral analysis. Ethanol is the best solvent for the spectral analysis since it is achieved and transparent in UV and visible region. Hexanes and the other hydrocarbons can be used because these are less polar and have least interactions with the molecule under investigation. For ultraviolet spectroscopy, ethanol, water and cyclohexane are the best solvents. The position as well as the intensity of the absorption maximum gets shifted for a particular chromophore by changing the polarity of solvent. By changing the solvent here, that is with a change in a pH, whether the acidic or the basic solvent, we have observed appreciable change in spectral properties of the drug, that is, chemical structure provided contain ionizable functional group. Paracetamol contains phenolic group which is ionizable in the presence of the alkaline solvent. So, change in a lambda max and absorption intensity occurs as compared to paracetamol in acidic solution where structure remains unionized. The choice of the solvent to be used in ultraviolet spectroscopy is quite important. There are the criteria. So the first criteria for a good solvent is that it should not absorb UV radiations in the same region as the substance whose spectrum is being determined. Usually, solvents that do not contain conjugated system are most suitable for this purpose. The second criteria for the good solvent is its effect on the fine structure of an absorption band. A non-polar solvent does not form hydrogen bond with the solute, and that the spectrum of the solute closely approximates the spectrum that would be produced in the gaseous state, where fine structure is often observed. In a polar solvent, the hydrogen bonding forms a solute and solvent complex, and the fine structure may disappear. The third criteria is it should be less polar so that it has a minimum interactions with the solute molecule. And the last criteria for a good solvent is its ability to influence the wavelength of ultraviolet light that will be absorbed via stabilization of either the ground or the excited state. Polar solvents do not form hydrogen bonding readily with the excited state of the polar molecule as with their ground state. And the polar solvent increases the energy of the electronic transition in the molecules. Polar solvent shifts the transition of the N to the pi antibonding type to a shorter wavelength. On the other hand, in some cases, the excited state may form stronger hydrogen bonds than the corresponding ground state. In such cases, a polar solvent shifts an absorption band to a longer wavelength, since the energy of the electronic transition is a decrease. Polar solvent shifts the transition of the pi to the pi antibonding type to longer wavelength. So, there are the various types of the transition. These are arranged here with the increase in the energy level. These three are the occupied level. These two, pi antibonding and the sigma antibonding, these are the unoccupied level. So, here is the transition of the sigma to the sigma antibonding. So, this is the type of the transition as a sigma to the sigma antibonding transition. Here is a transition of the sigma electron to the pi antibonding. So, this type of the transition is called as sigma to the pi antibonding. In the third one, here is a transition of the pi electron to the pi antibonding. So, this type of the transition is called as a pi to the pi antibonding. Next one, here is a transition of the n non-bonding electron to the pi antibonding electron. So, this type of the transition is called as a n to the pi antibonding transition. And the last one, here is a transition of the n electron to the sigma antibonding. So, this is called as a n to the sigma antibonding transition. So, this is the energy level. So, the n to the pi antibonding transition which are occur in a carbonyl type of the compound, n to the sigma antibonding which are occurred in a oxygen, nitrogen, sulfur and a halogen compound, pi to the pi antibonding transition which is occurs in a alkene, carbonyl compound, alkyne, azo compound and so on. Sigma to the pi antibonding transition which is also occurs in a carbonyl compound, and sigma to the sigma antibonding transition which is occurs in a alkane and saturated hydrocarbon. Now we have to see exact the effect of solvent. The position as well as the intensity of absorption maximum gets shifted for a particular chromophore by changing the polarity of solvent. By increasing the polarity of the solvent, compound such as dienes and conjugated hydrocarbon do not experience any appreciable shift. Hence, in general, the absorption maximum for the non-polar compounds is usually shifted with a change in the polarity of the solvent. Alpha, beta unsaturated carbonyl compound shows two different shifts. First one, n to the pi antibonding transition. This type of transition is less intense and also called as a R band. So, R band, that is the absorption R band, moves to a shorter wavelength by increasing the polarity of a solvent. And the reason behind this is the non-bonded electrons on the oxygen atoms that forms hydrogen bonding with the hydroxylytic solvent. The hydrogen bonding formation lowers the energy of the n electron. Thus, a distance between the n to the pi antibonding level becomes longer. So, more energy which is required for the transition of the n electron to the pi antibonding. So, more energy, that is in lower wavelength, because there is an inverse relationship exists between the energy and the wavelength. So, the absorptions will shifted of the R band to a lower wavelength. That is called as a blue shifts. The amount of the blue shifts has been used as a measure of the strength of the hydrogen bonding. In a n to the pi antibonding transition, the ground state is a more polar. Ground state is a more polar as compared to the excited state. The hydrogen bonding with the solvent molecule occurs to a lesser extent with the carbonyl group in the excited state. For example, acetone absorbs at 279 nanometer in N-hexane, while in a water the lambda max is occur at 264.5 nanometer. Now we have to see the pi to the pi antibonding. This is the second type of shifts, pi to the pi antibonding transition, which is more intense. This is called as a K band. The K band, that is absorption K band, moves to a longer wavelength by increasing the polarity of the solvent. And the reason behind this, the pi antibonding orbital is more polar as compared to the pi orbital. So, when solvent polarity increases, hydrogen bonding takes place to a larger extent at the excited state than that of the ground state, because pi antibonding orbital is more polar, and polar solvent easily form the hydrogen bonding with at a polar state, and the pi antibonding orbital gets more stabilized than the pi orbital. This lowers the energy of the pi antibonding orbitals. So the distance between pi to the pi antibonding orbital is a decrease, that is a load. So if the distance is a decrease, means lesser amount of energy is required for the pi to the pi antibonding type of transition. And if lower energy is required, transition will occur at more or a higher wavelength. So in short, the increase in a polarity of the solvent generally shift N to the pi antibonding type of transition and N to the sigma antibonding transition bond to a shorter wavelength, and pi to the pi antibonding bond to a longer wavelength. Now we have to see the procedure for the preparation of the pure drug solution. So weigh accurately 50 mg of the pure paracetamol powder, transfer this into the 50 ml capacity of the volumetric flask, then pipette out 10 ml of the 0.1 normal HCl solution and transfer into the same volumetric flask. Sonicate the solution for the 5 minutes and dilute up to the 50 ml with 0.1 normal HCl solution, and then make a label as a standard stock solution of paracetamol. After that, mix well and filter with a Whatman filter paper. Then pipette out 5 ml from the filtrated standard stock solution and then transfer into the 50 ml capacity of the volumetric flask. After that, dilute up to the 50 ml with 0.1 normal HCl solution. So this is the final dilution of the standard paracetamol solution, and make the label on the same volumetric flask to avoid any confusion. After that, record the spectra by taking 0.1 normal HCl solution as a blank. Then similarly prepare the standard stock solution and final dilutions of paracetamol by taking 0.1 normal NaOH solution, ethanol, hexane and benzene as a solvent, and then record the spectra by taking 0.1 normal NaOH, ethanol, hexane and benzene as a blank solution respectively. And finally determine the maximum wavelength of the paracetamol in all these solvent and report the results and conclusion. So this is the observation table. Here, write down here we have to fill this observation table. This lambda max and the absorbance of the solution, these two type of the value you will get from the UV spectrophotometer. And then you have to write down the results and conclusion. So these are the references. Thank you all of you.